Welcome back to ACER Explained. In this series, I'm going through Section 3 of the ACER Practice Test booklet. So bring that up in front of you if you don't have it already so that you can follow along. In this video, I'm going through questions 25 to 27, so that's Unit 8, and I'm identifying prerequisite knowledge, as usual, identifying reasoning skills that you might need, and the bootcamp resources that could help with this. So looking at the stimulus, we're given quite a short stimulus. It's just about the radio transmission, and we're given a formula or the distance that can be traveled by light in a year, which is 1 light year. And let me just write that out. So we're told that this is 1 times 10 to the power of 16 meters. And we're told that the invention of radio transmission was around 100 years ago. Question 25 is asking us what the current diameter of the radio bubble would be. So say that this point here is Earth, and this is the radio bubble, right? And over 100 years, our radiation has traveled this far. Right? So we want to figure out how far this is. So the speed of light is 1 times 10 to the power of 16 meters. So that's how far light can travel in 1 year. So if it was 100 years, then we would basically just have to multiply this by 100. And so simplifying this, we would get 1 times 10 to the power of 18. However, this is just representative of this radius, and we're being asked for the diameter. And so that we would have to multiply that by 2. So then the answer we would get here is 2 times 10 to the power of 18. And the answer is B. So for this question, you did need to know a little bit that radio waves are a form of light so that you'd be able to use the light year kind of formula for this calculation. However, even if you didn't know that, there's kind of enough information there for you to infer because the values and formula that you're given are limited. And so when you calculate the diameter of the radio bubble using the light year, you get the correct answer anyways. So even if you didn't know that radio waves are a form of light, that's something that you could have inferred just based on the amount of information that they've given you and the kind of information they've given you. So the resources that could be helpful for this are the bridging course on optics and light, but then mostly the acceleration class on calculations and formulae. So question 26 is asking us about the intensity of the signal. So it's saying it's difficult for extraterrestrial life to detect the signals because signals lose intensity at a rate inversely proportional to what? So let's think about this logically. If we have Earth here and you have signals that are going out, right? Your signal is going to, that's a terrible circle, but your signal is going to become weaker as it leaves Earth, right? And so if you're looking at the radius getting bigger, so it's kind of like when you have a bit of a gradient happening and it gets fainter and fainter as you go out, right? And so if this was a 2D circle, then the kind of rate at which the signals lose intensity would be inversely proportional to the radius in terms of the surface area or the circumference of this circle, right? Because it's from here, the signals that are concentrated here, they're going all the way out and spreading across this circumference. Now we have to think about it in terms of 3 dimensions because obviously our Earth is 3-dimensional, and so the way that the radiation is going to leave the Earth is going to create a 3-dimensional sphere around the Earth. And so in our 2D model, similar to how the radiation would spread along the circumference of the circle, in our 3D model, the radiation would spread along the surface area of that the surface area of that sphere. And that's why I have this formula up here. So the surface area of a sphere is calculated by taking 4 pi r squared. And now we're not looking for a specific value, so we don't need to actually use this for anything, but we're looking for the kind of intensity in proportion to the radius. Okay, so either the radius, twice the radius squared, or the radius cubed. And so we see here that in our formula, we have to use radius squared. And so just looking at proportionality, we're going to be losing intensity of our signal inversely proportional to r squared. And it's inversely proportional because the larger the larger the surface area gets, the lower the intensity. So that's why it's inversely proportional. And so that's why the answer here is C. So for the previous knowledge required here, you would have needed to know the surface area of a sphere, those formula. So the formulae for all of these different areas of different kinds of shapes are really important to know. That's just your basic maths knowledge, and that you can get from one of our bridging courses on maths. The reasoning skills used were calculation and formula, and being able to infer things from formulae without actually having a specific value. That's very important. And so the bootcamp resources are as follows: the bridging course on optics and light and on maths, and the acceleration class on calculations and formulae. All right, question 27 is a little bit tricky at first sight, but it's all about proportions. So what I would do is I wouldn't even try to kind of like go through the entire like formula, deriving all of this stuff. I would just think of proportions and try to figure out the correct answer based on that. Okay, so you have two signals of the same frequency. They're transmitted from the Earth, and Q has 100 times as much energy as P. And so it's asking about where they can be detected. And so that refers to the intensity. So remember in the previous question, we have intensity decreases inversely proportional to the radius. So intensity decreases as radius squared increases, right? Because of the surface area of the sphere. And so we're asked to assume that there's a minimum intensity at which Q and P can be detected. So it's basically saying that what's the very border of the sphere where Q and P can be detected, right? So thinking about the energy levels, Q has 100 times as much energy as P. So say this is our Earth, and then we have, this is a terrible sphere, but bear with me and pretend these are concentric. So you have two kind of borders where it's the minimum intensity of radiation. So because Q has 100 times much energy as P, you would assume that Q goes further and it can be detected further away. P is less intense, so the intensity of P dissipates quite early. But now we just want to figure out what's the relationship between Q and P and the intensity. And that's where our inversely proportional relationship comes in. So in terms of the proportions, Q can be detected up to 10 times as far as P, 100 times as far as P, or 1,000 times as far as P, or the same distance as P. So we know that it's not the same distance as P because it has 100 times much energy, so it's going to go further. But in terms of how far it is, we don't need to think about the actual proportion because we're already told that Q is detected further than P, right? All of these scenarios, Q is detected further than P, so we don't really need to worry about the proportion, the fact that it's inversely proportional, we just need to think about the r squared value now, okay? And so if you have 100 times as much energy, so 100x, and then P has just x, right? And we're relating this to r squared. We want to find out r. We don't want to look at r squared. That doesn't really tell us anything about the actual distance, right? What tells us about the distance is the radius. And so we want to square root these. So square root of 1 is going to be 1. So what I'll do here is I'll go r for q and then r for p. So the square root of 1 is just going to be 1. And the square root of the square root of 100 is going to be 10. So when you're comparing the radii of P and Q, you see that the intensity or the radius is going to be 10 times as much for Q than for P. And so that's kind of how I'm using proportionality, just to compare the two, rather than completing an entire set of calculations where I would need a lot of assumed knowledge for that. So then the answer is B. So this question was all about proportions. And so the reasoning skills used here are the calculations and formulae and also proportions. Previous knowledge was the one from the previous question, which was the surface area of a sphere. And the bootcamp resources that can help with this are the Maths Bridging course and the acceleration class on calculations and formulae. And that brings us to the end of this unit. Please like, share, and subscribe for more GAMSAT help. We really appreciate your feedback. We have our Instagram here at Thank Flip GAMSAT and our podcast, Thank Flip GAMSAT Nurses Doing GAMSAT, if you want to hear more from us. All right, I'll see you in the next one.